Okay, in this section, we're going to discuss some things that you can do with data that more adequately or accurately describe a signal. Now, we talked in a previous section about basic measurements. Basic measurements basically being defined as the mean, the RMS, and the variance of a signal. But here's an example where we have two signals that are clearly different. These are two different EEG segments. They have the same mean, RMS, and variation, but we can tell by looking at these that they're clearly different. So the question is, how can we get a better description of the signal? And one of the ways is to look at how to describe signals through data transforms and other ways of looking at signals. So, for example, we'd like some other method that would capture the differences between these two and other signals, and preferably be able to quantify what these differences are. And one way to do that is to use other functions or waveforms that can be used to describe signals and their differences. Now, in signal processing, functions fall into two categories. The first category is data, which would basically be waveforms and or images. And the second category are functions that operate on data. So transformations are basically operators that are used to modify data or operate on data. And transformations are used for three basic reasons. One is to improve the data quality by removing noise. So this example, we might use a filter, a digital filter that we would use just computationally to remove noise from our signal. Another application is to make the data easier to interpret, and the classic example of this is to take a Fourier transform of the data so that you can see what the signal looks like in its frequency components. And then the third reason is to reduce the size of the data by removing unnecessary components. The wavelet transform does this, as does principal component analysis. Both of these are data reduction techniques. So in this particular section, we're going to talk about what kind of transformations we use and then define a couple of them. Specifically, we're going to start with single observation data. But in general, you have two different data set types. You have single observation data. So this would be, for example, where you're monitoring something like heart rate, respiration, your cardiac pressure, etc., where you have one channel of data and you're just making a single observation at a time. The other example would be multiple observation data. In this case, you often have many channels, or in the case, for example, of functional MRI, you would have many pixels or volumes of interest within the brain that you're monitoring as a function of time. So you may have 256 or more channels that you're observing simultaneously. So the basic transform that's used depends on which kind of data observation, and sometimes these overlap. So for example, in a single observation data set, there are two different kinds of transforms that are generally applied. One category is called correlation-based, and the other category is called convolution-based. So correlation-based transforms would be transforms like the Fourier transform or the continuous wavelet transform, whereas convolution-based would be filtering or the discrete wavelet transform. So we're going to first discuss correlation-based type transforms so that you can see, first of all, what is correlation and what happens when we take a correlation-based transform. Under multiple observation data, you might have things like signal averaging. You might also have what's called principal component analysis. A couple of different ways to do this. Ensemble averaging is just a repeated averaging of multiple observations of signals, so that you're looking for some background phenomena buried in noise. Noise reduction is another technique. Sometimes you will do on multiple observation data correlation-based approaches per channel or per observation before you do some of these other things. So sometimes the categories on single observation data are applied to individual channels on multiple observation data. So let's look at how we might compare waveforms like the two that we saw that might give us a better indication of similarity between signals. And so first we need to describe correlation. So basically correlation seeks to find a way to quantify how much one function or signal is like another. So correlation-based approaches all involve taking the sum of a sample by sample product of the two functions. So R here is the correlation. And notice that basically it's equal to the sum over all of our data points of the nth x data point times the nth y data point. So n would be one data set, and y would be another data set or observation, or even another completely different type of data, and we're just wanting to find the correlation between the two. So, for example, it would just be the first data point in x times the first data point in y times plus the second data point in x, second data point in y, and so on. So RxY is used to indicate correlation, and x and y indicate what's being correlated. Now, there are different ways to normalize this data because obviously if you have signals that range from millivolt to volt range, and you have different types of signals and they have different units, we'll want to normalize, and different data record lengths, because if I have a 2,000 point data set, that might be different from a 20 point data set. So there are different ways to normalize this. One example would be to take this sum and divide it by n, the total number of points in the data set. So we can also visualize, if we have a data set or a data sequence X, and it has n components to it, or n data points to it, we can think of that as a vector, where the total dimensional space of that vector is the number of data points. So for example, if we're specifying position, which is the easiest to visualize in XYZ space, then we would just have a three-dimensional vector, and that would the vector would represent a direction in XYZ space. If we go to more than three dimensions or three values in our vector, then we have an n-dimensional data set, and it gets harder to visualize. But basically, it's the same phenomena. We just can't, as humans, visualize something more than 3 dimensions. So, for example, if our data sequence was 2, 3, 2.5, we can easily visualize that as 2 in one direction, 3 and 2.5 in the other directions. So sometimes this is a very useful way of thinking about the representation of data sets. And one reason it's useful, and right here we're just going to think simply in two-dimensional space. We've got some figures in two-dimensional space, but you need to understand that this can be generalized or extrapolated to an n-dimensional space. The reason it's useful is that in two-dimensional space, for example, we can visualize, here I have two different vectors, x1 and x2. And for example, we can visualize here in this case, when x1 and x2 lie on the same line, then basically they're completely similar. One is just linearly scaled compared to the other. If x1 and x2 are close to the same line and have a small angle between them, then we can see that they're highly similar and the angle between them is small. If the angle gets larger, then the similarity decreases. Now, how do you get a quantification of this similarity? Well, if we were to somehow project x2 down onto x1, we would have, for example, x2 is a two-dimensional vector. It has a dimension in the direction of x1, and it has a dimension orthogonal or perpendicular to x1. The relative amount of x2 that is in the dimension of x1 gives us an indication of how similar these two signals are, or these two vectors are. And when we get to the place where x2 makes an angle of 90 degrees with x1, we can see that there is no projection of x2 onto x1. It basically projects only as a single point in space. So these two vectors would be completely different. They would share no common direction. So the projection of one vector onto another is basically found by taking the scalar product or the dot product between two vectors. This is sometimes also called the inner product. And the mathematical notation for this are these funny shaped brackets. And basically, it's just the multiplication of the x vector and the y vector component by component, which you see looks very similar to what we described as correlation. So the scalar product can also be called the inner product, the standard inner product, or the dot product. So the scalar product results in a single number, not a vector. And we can also define it in terms of the magnitude of the vectors and the angle between them. And this can be proved through geometry and trig. We won't do it at this point. But basically, the scalar product of x and y can be equal to that sum that we saw on the previous page. But we can also define it as the magnitude of x times the magnitude of y times the cosine of the angle between them. So if you have an undergraduate engineering degree or took a physics class, you recognize this as the dot product between two vectors, where theta is the angle between these two vectors. Now there's no reason mathematically why you can't have more than two dimensions here. So we can actually have n dimensions. We can actually have an angle between these two n-dimensional vectors. So projection is an excellent way to compare two signals or to compare one signal with a probing or a test waveform. So in MATLAB, we can get the scalar product with the simple sum command. So we're basically saying we want to sum x times y. This dot is placed here so that MATLAB understands you want to do the multiplication term by term instead of vector or matrix multiplication. So here's an example where we're asked to find the angle between two short signals that are represented as vectors and to give the angle in degrees. Here are the two signals, and they're very short, so since they are short, we want to plot the two vector representations in 3 dimensions. So basically, to solve this, we want to construct the two vectors in MATLAB. We want to find the scalar product using the last equation, the angle equation. And when we multiply the two vectors together, we want to use MATLAB's dot star operator so that we're sure we're doing that point-by-point multiplication. So the solution is that the magnitude of a vector can be found by taking the square root of the sum of squares. And we can basically take this angle equation and solve it for cosine theta. So cosine theta will be the inner product divided by the magnitude of x and the magnitude of y. And so we can get theta by taking the inverse cosine of that. And because this is a short data set, we could actually do this analytically by hand. But here's the MATLAB implementation. So when you want to set up an array or a vector in MATLAB, you do that with square brackets. And in this case, we've generated a column vector because there are commas between the numbers. So we have x as a column and we have y as a column. And then we take the inner product or the dot product by taking the sum of x dot times y. Then we take the magnitude of x by taking the square root of the sum of all of the x components. And we find the magnitude of y by taking the square root of all of the y terms squared. And then basically this formula, this line of command implements that formula that we saw on the previous slide. So the cosine of theta, basically you take the dot product and you divide it by the magnitude of x times the magnitude of y. Sorry, let me go back. And then you find the angle by taking the arc cosine or the inverse cosine of the cosine theta term. MATLAB defaults to giving you angles in radians. So if you want to convert that to degrees, you take your output and you multiply by 360 over 2 pi. Now the 3D plot, basically plot 3 just gives you a plot of the vector point x1, x2, x3. And then in this line, we're plotting the vector line. So this 0, x1, 0, x2, 0, x3 gives us the x, y, z of the line. Here's the y vector plotting the endpoint, and here's the line of the y vector. And then here's the way you put a title on a graph in a MATLAB plot. This hold on command, what that does is you now can use multiple plot commands, and MATLAB remembers the previous plot command and just holds the graph. So here's what that looks like. Here's our dots that we plotted with the one command, and here's the line that were plotted with another command. You can see that the angle between these two vectors is 26 degrees. If these were signals, this is a fairly small angle, and so there would be some correlation between these two signals.